This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 97. Hope everybody's doing well. Thanks for taking time out of this busy May for weather events. Today's presentation title, Making Use and Sense of the ABI Fire Detection and Characterization Algorithm Data. The presenter, Chris Schmidt, the ABI Fire Detection and Algorithm Developer and Researcher from the Cooperative Institute for Meteorological Studies in Madison, Wisconsin. Our facilitator for today, Matthew Foster, the Science and Operations Officer at the Weather Service Operations Proving Ground. Just a few reminders before we get started. First and foremost, hope everybody saw the first light image from GOES 18. If you haven't, you can check out the NWS Insider if you're part of the Weather Service, or head over to nesdis.noaa.gov to see the first light imagery. GOES 18 will begin its journey to near the GOES West position starting next week, and will continue the post-launch test activities in the western orbital slot, or near the western orbital slot. Just a few reminders, as you heard, that this session is being recorded. There will be an opportunity for Q&A after the presentation, particularly interested in questions and comments from our forecast offices and regional headquarters. Please post them in the chat and we will field them through there. However, if you have a longer question or comment about how this applies to forecast office operations, you'd like to verbally express that, please indicate as such in your comment. We'll certainly give you that opportunity. We're also encouraging attendees, if you're signing in with an office account and you ask a question, please use your full name when asking the question in the chat. That way we can get back in touch with you a little easier if we need to. We're always looking for future presenters. We're headed toward 100 satellite book clubs. It's really been a great series, and we would like you to contribute, particularly if you're at a forecast office, you have something you want to share with the field. Maybe it's something you don't have an answer to and you just want to discuss it. We think that's great for the Satellite Book Club. So please consider that and get in touch with us if you would like to be part of this series. And if you're looking for training materials, either that you may be unaware of or that are unavailable, Brian Mott, the Office of Chief Learning Officer, can help with that. I'd like to thank our TowerS team, particularly Kashad Bowman, who does all the behind the scenes work to get us where we are each and every Thursday. The Office of the Chief Learning Officer, the GOES-R and JPSS programs, as well as our facilitator, and all of you for joining us. Without further ado, I'd like to formally introduce Chris, who, as I already mentioned, is a researcher at the Cooperative Institute for Meteorological Studies at the Space Science and Engineering Center at UW Madison. He started with the Biomass burning team in 2002, tasked with making the WFABBA operational, and has been the algorithm lead for the Fire Detection and Characterization Algorithm for the ABI. Currently, Chris is working on updates to the FDCA, collaborating with NOAA on its fire initiatives, and developing his notions of a next generation fire algorithm, which is a high priority for the agency. Chris, welcome back to the book club. We're glad to have you.
Thank you, Jordan. I would like to start by explaining what this presentation is. It's a little bit different than presentations I've given in the past. It's, first of all, done on short notice, but also I'm trying to focus on feedback I've gotten from forecasters in particular, questions that we've received, including one that was just a week ago, to try to address some of those issues. And I want to encourage folks, if they think I've missed something that they've run into, to bring it up afterward. We can maybe talk about it a bit, or I can reach out to you later. So yeah, I'm sure most of us are more or less familiar with ABI fire detection at this point, but just to talk about some of the physical basics. This loop, by the way, is the Marshall Fire from last December, and that's all 16 bands of the ABI. So the current FDCA, which is NOAA's operational algorithms based off of the Wildfire automated biomass burning algorithm that was developed by Elaine Prins at SSCC starting in the 90s, and became the old GOES operational product and was transitioned to ABI. And it provides the detections. It provides fire rate of power, fire size, fire temperature at the full resolution, temporal and spatially. And when I say full resolution spatially, I mean of the 3.9 micron band. Fire detection relies primarily on that band, which lies at the junction between the thermal emission and the reflection. That is conveniently enough where fires are most strongly represented. But as the loop on the right shows, a fire signal can be seen in pretty much any band. Most likely won't see them in bands 1 through 3, but it has happened. One rare case where we even saw it in that blue band. It was a very, very hot propane explosion, but it does happen. Most natural fires, however, wildfires, you'll tend to see them in bands 5 and up, and maybe sometimes down to band 3. I'll talk more about that because it's relevant to some of the issues I'll discuss later. In this case, with the Marshall Fire, as we know, it grew pretty fast and moved from the west to the east, and was pretty damaging. Probably the biggest impact from last December. And it used to be we didn't have fires like this in December, but this is becoming an annual thing. So what is fire characterization? We know the detection's important, but characterization matters too. Traditionally, we would provide, back in the old days, we were providing size and temperature for primarily users in South America. They were the first users of fire products back in the 90s and early 2000s. And it was based on something called the Matson-Dozier equation, which is on the right, just using two unknowns and 2 equations to try to pull out the size and temperature fraction, the size fraction and temperature. And the bands we use are the 4 micron, and then we're using a long wave, traditionally 11 micron, but you can use the 10.3. You just need basically a clean window that's similar to the 4 micron that has a weaker response to fires, and preferably no reflection, which thankfully long waves don't have. There's a lot of users for this stuff. Most users these days are using FRP. Size and temperature are hypothetical representations of what produces the same signal. And I don't think it can be stressed enough to say, please don't rely on that for anything quantitative. It's not accurate. It kind of gives you a general sense of something that's really hot and small versus something that's just kind of warm and large, but it's very sensitive to the subpixel variations of the fires and even just correlation between the 4 and 11 micron bands. FRP is a better proxy for intensity, but as we'll see, even that has its issues. The other product that comes out of this that you get in AWEBs is the mask. And the mask was new last year, and the full mask tells somebody on every pixel what the decision of the algorithm was. In AWEBs, we just include the fires themselves, the 6 fire categories. And those are processed fires. They have all the properties, are our highest confidence. We also have a high confidence in saturated fire pixels. Pretty much only fires saturate ABI. I really haven't seen much else do it. It will provide an FRP in the data files anyway. That's a low end estimate. However, you don't see that in AWEBs right now. Well, we're going to talk about fixing that. It was supposed to be in AWEBs and it is not showing up. It's being screened out. Same with cloud covered fires. They're usually fairly high confidence too, and they just look right. They look right in band 2, basically. Usually FRP is available in the data files. Again, it's not showing up in AWEBs right now. High probability fires are similar to process, but lower confidence. Those FRPs do show up in AWEBs. And then there's medium and low probabilities. Those are lower probabilities, and false positives become more and more common, and FRP becomes less and less common. So if you're looking at just FRP, you're not going to see the medium and low probability. They're screened out anyway. But even if you could see all FRPs, most of them wouldn't show up. So the mask shows you everything, and the FRPs show you most of what you should see. We'll get into that. One of the technical issues that comes into play here that I want to talk about up front is pixel spread. The satellite's telescope does an excellent job. We're making it look at 16 different wavelengths. We're making it scan across the Earth very quickly. And however, it's one telescope doing all that work. And for any given optical system, a point will look fuzzier as wavelength increases. That's just physics. We can't get around that completely. There's some attempt to do that with math, with the remapping, but it's limited by the fact that it's happening. This is somewhat illustrated with the Marshall Fire. And so this is one of those frames. I zoomed in closer to the fire and I put that red circle on where it's peaking in band 5. And then you can see in band 6 right next to it, the 2.25 micron, there's that bright spot. It's bigger, it covers a larger area. And that's because it's got a coarser resolution and you've got just a larger blur spot, a larger Aries circle as it's called, at that wavelength. And the same is true at the 3.9. If the response to the fire was equal for all the wavelength bands, it would look progressively fuzzier. However, because the fire response drops off, it looks about the same in most of those long wave bands. So you see that kind of black spot in the long wave windows showing the fire. So it's important to recognize this spreading issue because it's a complicated mixture of the optics, but also when you're looking at the 3.9, you are picking up things that are cooler than you can see in the 2.25 and the 1.6. So it's not just a simple answer of, oh, what the 1.6 shows is where the fire is. First of all, it's really hard to separate it during the day from the background. There's things smoldering at 600 Kelvin, 500 Kelvin, 400 Kelvin that we really want to know about, but they're not going to show up in those shorter wavelengths very well. But they do show up a bit more in 3.9. Another issue that's an important technical issue that we'll talk about is terrain correction. It's been developed, but it's not fully implemented yet. So you'll see an example of it, but it's not in the processing chain quite yet. And it begins with a high resolution data set, and we come up with corrected pixel locations. So this is just a GOES 16 band 2 image at 500 meters, just showing some mountains with snow on them. It's a nice, easy reference point. And then on the next slide, it's been terrain corrected, and you saw how it shifted to the southeast, which is basically toward the satellite. This is up in the upper west of the Rockies. Bitterroots, I believe it was actually. On the left of that is a representation. This is looking at those pixels in excruciating detail at the full resolution of the digital elevation model, which is, it's 30 meters basically. And that shows what those footprints really look like on the ground. They're very, very tortured in some cases in the high terrain. And that is something we need to be considering with algorithms. We're not doing much with that yet, anything with that yet, but this is something on the science side we need to work on because it is relevant to the detection problem, as we'll see shortly. And this is just an illustration that it works. VIIRS has terrain correction already, and so we can use it as a reliable reference. And on the left is the uncorrected ABI raw image in band 7, 3.9 micron, and then on the right, the corrected one, and the detected fires are plotted on there too. And you can see they line up much better with the correction applied. This particular case was raised by Wilfred Schroeder from SAB, concerned about the nav error when it's not technically nav error, but it's nav error as far as users are concerned, and we got to fix it. So there are a bunch of common questions that we'll reference here. Most products don't have to worry about the pixel level like fires do, but oh boy, fires do. And as I said, terrain's an issue for these. So some of the common questions are, one satellite sees a fire, but the other doesn't. Why is that? They'll see the same fire, but in different places. Well, we already answered that one. That's the terrain. The satellites assign very different properties to the same fire. Well, there's many reasons for that. I know there's a fire there, but the product doesn't see it, and it's not cloud covered. There's different reasons for that, including, for example, you're looking at FRP, and it is just screened out because of something we need to address in the processing chain. If you look at the mask, it shows up. And why am I getting particular false positives? So as far as why those disagreements are happening, the basic reasons are the terrain, as I've said already, atmosphere, small clouds and variations in transmittance, such as the optical path, are play a big role. They play a role in why those FRPs are different. We're not doing anything to really correct the FRPs. And for optical path, not really. We're not using a CRTM. That's coming in newer things, but it's not there yet. The wibble wobble, as I'll call it. The ABI is very stable, but there are subpixel motions, and because you've got those small fires moving around within that diffraction pattern, that changes what you read off the fire. Oh boy, that gets interesting. There's also phasing of the remapper, which is a subtle impact. I didn't really have a good example to show you, but it does happen. It's an interesting thing, depending on the time when the scan starts, down to the microsecond. There are details about how the data is remapped, and sometimes when you say your mesos start 57 seconds apart, that's the change in the phasing, as it's called. And if you pay real close attention, sometimes you'll see something should be a real sharp point, and it might split between 2 pixels in the next scan just a minute later. And that's what's happening. That's the remapper. So we'll look at several examples. Hopefully I don't burn too much time. I know I'm going kind of slow here. So Pine Creek fire. This was on that last July, there was a low intensity dry thunderstorm passed over the Snake River Basin. And at about 1 p.m., a fire was reported in Pine Creek Canyon, southeast of Julietta. And so this is just to set the stage. There's a canyon in the middle and some flatlands and other canyons around. And so here's what the loops look like. Now I had to make these from my own stuff. It's not AWEB's. We'll show you in a minute. But there's various fires happening. When the Pine Creek shows up, it'll be circled. There it is. And you can see how on the right is the mask, and the second panel is the 3.9. Between the 3.9 and the mask is a radiance difference with the long wave. Just different ways of looking at the fire. And we'll look at it in more detail in a second here, but you could tell that Ghost 16 actually had a better view than Ghost 17. Ghost 17 should see the fire better, given its position. But actually 16 has a better view of it. And to illustrate that, here we have a terrain corrected animation. Let's give it a second to load. And this is both 16 and 17. 17 on the left for the west, 16 on the right. That's the terrain under that. And the pixels have been corrected to overlay them on the terrain, so you can see they're following the contours of the canyon, for example. And there's long periods of time here where Ghost 17 doesn't see the fire and 16 does. There's no cloud issues. It's not clouds obscuring it really. This is all something else. And I will posit that it is terrain in this case. And to back that up, we'll look at this and say, okay, so those pixels are overlapping on the canyon pretty nicely, pretty fully. Sometimes 16 spreads a bit to the west, but that could be due to something else. Let's look at the canyon on a high resolution image. So this is the high resolution image from the satellite, and the western side of the canyon has all the vegetation and the eastern side is pretty bare. Now, if you're looking from Ghost 17, you've got an oblique angle on that canyon. You're not going to see the signal very well. Ghost 16 has a pretty straight on view. So it's not a surprise at all in this particular case that Ghost 16 had a better view of this fire, even though 17 would seem to be in a better position. This happens a lot in terrain. It's something we've got to deal with on the processing side more effectively and in a detailed way. And it's something you can watch for too when you're looking at things and trying to figure out why they're different. Another case is near Mesa, Washington. This is one that was brought to us just last week, brought to me. The GOES Fire Alert app that some of you use sent an alert about a fire near Mesa, which is just Bias Volcan. And he was questioning the disagreement readouts between the FRPs. And so that's the rough location of the fire. It's mostly agricultural. There's a little bit of non-ag land, but it's mostly ag or barren. So it's pretty flat. So terrain's probably not an issue. Here's the GOES 17 viz, and it'll put the FRPs on top of it from both satellites. And so the parallelogram that slants to the left is 16, the parallelogram that slants to the right is 17. And there's disagreement about when they both see it. There's disagreement about the magnitude. There's one there where the FRP is actually twice as high on one than the other, although it's also spread over 2 pixels on the smaller one. So looking at that in a little more detail, one of the less extreme time steps, The FRP from GOES 17 came in at 191 megawatts and 16 came at 153. 17's got a better view, maybe that makes sense. Strictly speaking, they shouldn't be that different actually if we were doing everything correctly and diffraction was on our side, which it never is. But these are reasonably close together. And we can attribute the differences maybe to optical path, maybe, but we need to look at this a little more because at another time, a few minutes later, GOES 16 has the higher FRP and 17 doesn't. And we saw there was a lot of variation. We also saw in the loop that there was a lot going on with those clouds. And so here's the band 7 for both satellites. 17's on the bottom and 16's on the top. Yeah. And you can see where the fires are, although it's not super clear with this enhancement, but we can tell they're there and we can follow it once we know where it is. But the background's shifting a lot. There's a lot of variation in that background, and that's due to those clouds. They're screening and they're reflecting. So they're making things complicated for us. They're reflecting some light because they're water clouds, and they're also screening the ground. And so they're complicating that optical path. And they are likely the primary culprits for the variation we're seeing with this particular fire. A lot of small Q moving through, and they're just causing us trouble. And I forgot to mention, and I don't know if it got put in the chat. Yeah, it did. There's a YouTube link for these things, for these animations, since I know that GoToMeeting can be a bit rough sometimes. Another detail that I should mention is that where the fires land, the diffraction pattern makes a difference. So the pointing issue. Now, when you look at those 3.9s, the pointing looks fairly stable, but when you zoom in on that band 2, which is what this background is, it wobbles a lot. So this is just, again, last week. It's the same day, but down in New Mexico. And you can see those snow color, those mountain tops and whatever other terrain are dancing around a fair bit. This is pretty common. That is affecting the fire because those fires are moving with respect to the pixels. It's mitigated somewhat by that airy spot I was talking about before, that diffraction, that kind of spreading. So it's not quite as bad as it looks in band 2, but it's still present. It's still a factor in why things are changing from frame to frame. The missing fire, sometimes you wonder why isn't there a fire there, and there's several reasons for that. One question I often get is how small of a fire can you see? And I tell them I don't know. The technically correct but unsatisfying answer is a fire that produces enough radiative flux to cause a sufficient increase in brightness temperature to exceed a threshold, be that your visual threshold or the one in the algorithm. We've seen burning houses. One of our participants in this call, in fact, alerted me to one. It was a great example, but it was only half a Kelvin increase. But trained humans can spot those kinds of things and tell people if they need to. Other times, algorithms will miss things for other reasons. This was a fire that happened near where I grew up. The top image on the right, the top satellite images on the right are from 2242, and below that is 5 minutes later. And there's a picture on the ground level that my father took for me, right between them. And it's got a good burn going on. It's just a prescribed burn. It's a few acres, a few dozen acres total with the smoldering portion. Flaming area was not very big at all. So the flaming area is like 1,000 Kelvin or so maybe, and the smoldering is 500-600. You can see there's the fire is visible to us, dead center in those 3.9 micron frames with the 2 different enhancements. The algorithm didn't see it, and there were a couple of reasons for that. One was some bugs in this version back in 2018, but also it was just kind of cold background, and we had set things so that they wouldn't look too hard in cold backgrounds, because gosh, why would fires happen in cold backgrounds? Well, that assumption is out the window these days. Looking at the New Mexico fires are going on right this week. This comes from just 2 days ago. This is the FRP view of New Mexico fires, and at first it looks reasonable. You got the GOES 16 FRP on top of the GOES 16 geocolor, and okay, you got hot spots lining up with plumes. However, we look at the mask, and it gets different. There we go. it fills in quite a bit. So that's what I meant when I was saying things were missing from the mask, or from the FRP rather, that we need to fix. All those saturated, those yellow points are saturated pixels. Those are definitely fires. They're burning. And a lot of those cloud covered ones are called cloud covered because the smoke is so thick. They're burning. There might be some pixel spread in there too, but look at the mask too, basically, is the moral of this story, at least until we get the FRP fixed. Looking at the same thing again for GOES 17, similar story. That's still the GOES 16 background, by the way. Should have made that clear on the slide. And it fills in. So, and here's the animation with the geocolor background. I can't show a geocolor without animating it, right? Right, Steve? Here's the mask, both masks on top of it. And so you can see that it's kind of chaotic because of that terrain. But they do agree pretty well in general as far as like where the saturation's occurring and what's happening on the edges and such. If I really wanted to show you a corrected loop for this, I just didn't have the time. Oh gosh, it would have been beautiful. But someday we'll be doing that. False positives. Initially we threw a lot of false positives early on, up until 25th of July 2019, my favorite day when we switched versions and things got a lot better. As it stands right now, you know, if you're looking at just those processed fires, especially if you're looking at size and temperature, you won't notice as many false positives. You'll see them, they'll happen for some of the reasons we're talking about, but they're not as common. They tend to be more common in lower probability fires. And they're coming from a variety of sources. A lot of times it's water clouds giving us trouble, or other reflections from the grounds like solar farms, or areas with high emissivity like bare fields, and sometimes thermal emissions from industrial activities like gas flares, cooling lakes, refineries, that kind of thing. I'm just going to step through an example of the different bands that highlights one of the cloud cases. So here's the mask on top of the visible in GOES 17. I just highlighted this little fire out in the middle of nowhere. It looks, at first glance, looks fine. It's low possibility, could be something. But if you look at just the visible band in the same spot, there's a small cloud there. And okay, let's look at the 3.9. If you look at the 3.9, it's not particularly remarkable. You don't see really heating or cooling, but you can tell that there is stuff going on with the you know, warm and cold as far as the terrain and the clouds. And we can see that when we switch to the 11 or to the 10.3. There's some alignment between what's warm and cold, but it's not perfect. That pixel looks a little cooler in the 11 or the 10.3, sorry. But if we switch back in the west, things look generally kind of warm and flat in a lot of areas. And then there we go to the east, or back to 10.3. You can see there's more texture there. So a couple things happening here. One is that the water clouds are reflecting some sunlight, so the natural cooling is being offset by the reflection. And that's why it looked flat in 3.9. And because it was lower in the 10.3, the algorithm flagged it as possible fire. And it wasn't smart enough to know because it doesn't look in time or very well in space for that matter at that resolution or at that wavelength, what might be really happening there. Solar farms are another thing that we deal with. I mean, I've shown this example in other talks, you may have seen it. This is just from a few years ago, looking over the southwest, and we can see as the sun marches across, solar farms light up. We got the particularly bright topaz on the left. That one distorts data up and down the column sometimes. They're tricky. They're not always so bright either, as the next example will show. This is in Minnesota. Whole bunch of solar farms lighting up imagery. To explain this imagery a little bit, you've got visible 1.6, 2.2 in the top row, then the 3.9, and brightness temperature difference with the 11, and then the 11.2, then mask, radiance difference, a rolling average radiance difference. And just the whole point is they're tough to find. They're not always super bright in the shortwave. They can be pretty dim actually and still produce a notable signal that we even pick up. And So that's something else to watch for. There's more and more every day. One has gone up near Madison just the last few months that I'm sure we'll have to screen out. And we're working on getting those screens into the algorithm, both the operational one and things to come. Speaking of which, looking ahead, there are a number of changes on the horizon for this algorithm. There'll be, and as more broadly, NOAA's fire efforts. Congress has put a lot of money into that, and things will be happening under the guidance of Mike Pavlonis and Yvonne Cesar and others. Things like a persistent anomaly mask to deal with solar farms and other repeat offenders, as well as terrain correction, should find their way into the algorithm and the EOPS feed. That broader effort, we'll see how that all manifests itself, but a lot will be happening. And some of the issues that I've talked about will be mitigated by the improvements that will be coming, but other things we'll never really be able to beat because optics is the law. And with that, hopefully I didn't go too far over time because all my clocks are hidden. And there's my contact information, the links for the video list and the channel. This particular background image was from Reno. I happened to be in Reno on the 24th of August. And it got pretty smoky all of a sudden as the Caldor fire blew in from the west. It was rather remarkable. And the loop there is from GOES 17, just showing the Caldor fire during some of the worst periods. We didn't really talk about the cooling issue because, GOES 17 should be going away this year later, but fires are not affected too much by the focal plane heating. So at least there's that. And with that, ready for questions.
Yeah, thanks, Chris. It was a great presentation. Want to encourage everybody to hang around. We have about 10 or 15 minutes here for discussion. Really looking for participation from the field, forecast offices, regional headquarters. Reminder, please try and use your full name in the chat when asking a question, and complete the feedback survey that either has been or will be posted in the chat room. Also remember, a week from today, we're going to have Dan Lindsay and Tim Schmidt. We'll be talking about the initial GOES 18 ABI imagery that we've seen. And if you have any questions about the SBC and what's going on here, get in touch with the Tower S team, Lee Byerly or Kashad Bowman will be happy to answer your discussion. So you can put questions in the chat, or you can just speak up and ask them right here. So I see Bernie is asked in the chat here, what is the fire radiative power? And additionally, how does the forecaster use and interpret it?
Well, there we go. Fire radiative power is the power output by the fire. That's that instantaneous energy, that joules per second that's coming out. The way we calculate it is we're using an approximation from the radiances because they're roughly linear to the power, to the temperature to the fourth power, which is the definition of fire radiative power. If I was more nimble, I could switch back to the slide. It's way at the start of the deck. But as far as how is it used, well, for forecasters, its best use is as intensity. That's really what it tells you. It's a good measure of intensity because, again, it's proportional to that radiance difference between the fire and the background. And interpreting it is tricky. You can generally say, based on the trends, it's getting hotter or it's calming down. But you got to watch out for that noise that could be due to those things like the small clouds and the shifting of the nav and those other things. It's kind of a mixed bag. For big explosive events, it's always very obvious. Yep, it's getting bigger. The FRP is shooting up off the scale, and that's where it's good. For smaller fires, it's trickier to interpret. both by the nature of the observation and just because smaller fires are trickier to interpret, especially when you don't know exactly what the ground looks like and what's burning.
Yeah, and that kind of dovetails into something I had jotted down here, Chris. And Bernie asked to follow up. People understand temperature pretty well. Why not just use temperature? And this is something in the OPG that we've run into before. And I think it might have been you, Chris, had a discussion with our previous director, Kim Runk, about the temptation to characterize a fire as getting hotter. And like you said kind of at the beginning of the talk, well, what the satellite is seeing because of things going on at the subpixel level, it could be, what you could see is maybe a smaller fire burning more intensely, or maybe it's getting bigger and filling the pixel more and causing the perceived temperature to go up. And maybe this is a little out of your wheelhouse, Chris, but if we don't know for sure that fire's burning hotter, what is a more proper thing, I'll say, that forecasters could say to message when they're seeing a perceived change in behavior of a fire on satellite?
Well, I would, to answer the question, why not use temperature? The temperature that we understand is not the temperature that's being reported. And again, this is a legacy thing. It was the size and temperature came from efforts to support the only users at the time who were in South America. The original ABBA ran over the rainforest. Basically, it was being used for monitoring rainforests to the point where I once had trouble getting into Brazil. It could have been because of my work on this. That temperature, as I said, represents this hypothetical beast. A real fire is a mixture of temperatures. It's got a fire front that's burning 900 to 1600 Kelvin, depending on what's burning and how intensely. And then there's most of the fires not burning as hot. The smoldering regions might be 500, 600 Kelvin, something like that, and everything in between. It's a mix. And so when we're looking for intensity changes or higher temperatures, we really want to know what that fire front is doing. And FRP kind of does tell you that, generally speaking, with the caveats I explained before. It reflects how energetic that fire is. And when you see big changes over time, increases over time, you can say, yeah, it's definitely blowing up. Or if it seems pretty stable, even if it's kind of noisy, if it seems pretty stable over time, it's like, well, it's burning, but it's not expanding rapidly. That would be how I would take it. In the future, we'll probably see those fire and temperature estimates go away because, as I said, they're confusing. And they're not even necessarily that accurate, because if you let the algorithm do what it does now, it will give you temperatures that are unrealistic, like over 2000 Kelvin. And there's not much that burns that hot. But the math works out so that those temperatures fit the values that you get. But again, there can be pretty big error bars on those radiances for the various reasons I've discussed. So we're probably going to move away from it unless there's a huge user demand to keep it, and then we'll have to try to find a way to make it better. And one way to make it better is to use more bands. We could use band 6. Three unknowns will make it better. Maybe even band 5, but that gets more complicated too.
Okay, Lee put in the chat here, there was an offline question about the availability of FDCA and AWEBs. And yes, the GOES Fire hotspot products are found under the derived products menu for full disk, CONUS, and the mesosectors. Just to follow up on that quickly, Chris, you said there were some issues with some of the FDCA products in AWEBs, and do you know, is there a timeline on those being fixed in AWEBs?
No, because Lee and I found them yesterday.
Oh, okay.
I didn't realize it was happening. I actually made changes to the algorithm to let FRP show up for more pixels because it was not showing up for really hot fires that people knew were there, because it was being screened out by the quality flag, and that's still happening. I thought that had been changed, so we're gonna work on that. We got to make sure we don't throw too much in at the same time, but we'll get it sorted so that it gets better. But yeah,
Okay.
all the FDCA products are in EWIPS now, which is great. Even the mesos, that started a year ago, pretty much a year ago to the day practically. And that was a long fought battle to get that.
Yeah, and those the mesosectors would be a really great application of this. Steve Miller said he had a question he'd like to get. I don't see any other forecaster questions right now, Steve. So if you want to go ahead.
Okay, yeah, thanks. Hey, Chris, nice presentation. Congratulations to you and Elaine and your team actually over the years for all the great work you've done in this area. And as we see, we're getting into a paradigm now where I guess, this is becoming even more relevant than it already was. So it's only going to become more and more important to get all of these, challenges addressed. One quick comment on the fire radiative power. I'm aware that it is used in some cases to initialize the smoke plume and injection height in models like WRF S-Fire and maybe Hirsch smoke.
Yep.
So I'm aware that FRP is used maybe in an empirical way to do that. So that's another kind of practical quantitative application for smoke forecasting that we've seen shown more prominently on the news in recent years. But my question to you had to do with the wobble, which I thought was really interesting that we're still having to deal with these things even with the new generation satellites. I wondered, is there an opportunity to do something like a pre-processing correction step where maybe between two images you throw out all the clouds using a cloud mask and then do kind of like an energy minimization by iteratively shifting the long scan and the long track, a difference between those two, realizing that there is a little change in the background as depending on what band you're using, the temperature or the reflection changes, but you'll still get some kind of local minimum perhaps, at least if you went to a certain scale. If you zoom in too much, you might lose that ability to do that. But I just wanted to know your thoughts on addressing the wobble. Is it feasible, and is anything being looked at in that kind of train of thought?
Well, I've been thinking about it a lot, involved with another project where it's even more important. But I think there's an opportunity, but there's a kind of a trade-off occurring for us, and that pixel spread I was talking about is mitigating the observability of the wobble, shall we say, at 3.9. And I don't have a very solid sense of what exactly that diffraction pattern looks like. Hoping I can maybe, now that I understand it better, maybe I can get some information that'll help me see what it looks like exactly, like how does it relate to the nominal footprint. That matters a lot too, because if it's really sharp, shall we say, if most of your signals within your nominal footprint, that wobble really shows up like it did in the 0.64, the 500 meter was moving around quite a bit. But with the 3.9, because it's broader, if you pay real close attention on a totally cloud-free scene, it doesn't show up as obviously because it's just blurrier. So will we even really get a lot of benefit? I don't know. But because FRP is so sensitive to those slight changes of, fractions of a radiance unit, it might show up there more. So it's a maybe. It's a qualified maybe. I don't put that super high on my list right now compared to other things, but I think understanding the terrain under the pixel, at least the general terrain under the pixel, is much more important in some respects for us, because I didn't even mention that we got places we can't see with any given goes. There are places that are screened out, and we can estimate where those are, so we better understand what's happening. Had it not been for clouds, there was another fire in the Colorado mountains at the end of December that would have been a beautiful example of this, because we had ground truth showing it was happening in a place that GOES 16 could not see. Unfortunately, there were clouds blocking GOES 16's view as well, but GOES 17 had a great view of it. So it does happen, and it's important when fires are small. If you're trying to use both satellites to validate each other, it may not be possible.
Yeah, thanks,
Okay.
Chris. That's really interesting to think about. You know, you have your digital elevation mask that kind of gives you an anticipation of where those problematic pixels may reside. You might even be able to use that in a priori sense to, I don't know, think about modifying your detection limits based on what you think you can or can't see at a given location. But with that wobble in place, that's more challenging.
That what you just said is exactly what I've been thinking we should do. And I see Bernie asked another question regarding that wobble. Is that natural variability due to the fire behavior? And maybe it is. That's part of the challenge. When you're looking at the meso data, you can be a little more confident that the fire isn't radically changing minute to minute. And then that wobble can become a little more apparent. When you're looking at the 5 or 10 minute steps of Conus or full disk, the fire can change a lot in 5 or 10 minutes. And the changes could be because of the fire itself. It could be the clouds, the wind picked up and changed the fire. Sure, it happens. It's tough. Are winds well predicted in mountainous terrain? Not exactly. There's others who can answer that question better than I could, but I know it's a problem for firefighters.
All right, but we are past our 11:45 Central, 12:45 Eastern ending time here. So I want to thank you, Chris, for a great presentation. I think we're doing a lot more with fire detection from satellite now than we've ever done before, and there are more great things to come. So I'll turn it back over to Jordan for some closing remarks.
All right, thank you so much, Matt, and I really appreciate Chris Schmidt for putting that presentation, very relevant presentation together in relatively short notice, as we had to find somebody for this week. Next week, Thursday, May 19th at 12 noon Eastern time, we're going to have Dan Lindsay and Tim Schmidt, who are the program scientist and meteorologist with NESDIS STAR ASPB respectively, to talk about the early GOES 18 ABI imagery. So if you are a forecaster, particularly out west, you might be interested in that. Please join us next week. In the meantime, if you need to contact the Tower S team for anything related to the fire products you heard about today or anything else related to satellite imagery, you can see the email addresses there on the screen, or reach out to the Tower S team via the NWS chat. With that, I really appreciate all of your attendance today and the good audience participation in the Q&A following the presentation. Thanks again to Matt and Chris, and of course, our Tower S team, Lee and Kashad behind the scenes. Take care, and we'll see you again next week. Bye now.